Hello, cosmic travelers. Welcome back to the channel, or if you're new here, a very special welcome to you. For a moment, I want you to close your eyes and picture the most terrifying, awe-inspiring object in the universe. A place where gravity is so strong that not even light can escape its pull. A cosmic vacuum cleaner that swallows stars whole. You're picturing a black hole, right? We all know about them. They're the ultimate monsters in the dark of space. But what if I told you that the equations that predict those monsters also predict their perfect polar opposite? Not a devourer, but a fountain. Not an end, but a beginning. A place where the universe doesn't suck things in, but violently, beautifully spews them out. A place where the rules of a black hole are played in reverse. Today, we are talking about the most hypothetical, the most elusive, the most beautifully bizarre idea in all of theoretical physics, the white hole. So, if your brain is ready for a journey to the very edge of what is known and what might be possible, hit that like button, subscribe for more deep dives into the fabric of reality, and in the comments below, let me know where in the world you're watching from and what time it is for you right now. It's always fascinating to see our little community of curious minds spanning the globe. Now, let's start with the most basic question: what is a white hole? In the simplest terms, it is the theoretical mirror image, the inverse, the exact opposite of a black hole. Think of it as a cosmic yin to the black hole's yang. While a black hole possesses an event horizon, a point of no return from which nothing, not even light, can escape, a white hole has an event horizon that is a point of no admission. Nothing from the outside universe can ever cross in. But from its interior, energy, matter, light, and information can and do escape, erupting outward into the cosmos. If a black hole is a bottomless drain in the fabric of spacetime, a white hole is a pressurized geyser. A black hole pulls, a white hole repels. A black hole is defined by ultimate absorption, a white hole by ultimate emission. This isn't just a poetic metaphor, it comes directly from the cold, hard mathematics of our most successful theory of gravity. And that brings us to the who and the how. To understand where white holes came from, we have to rewind over a century, to the seismic shockwaves sent through physics by a single man, Albert Einstein. In 1915, he published his general theory of relativity, which completely revolutionized our understanding of gravity. Forget a mysterious force pulling at a distance. Einstein proposed that mass and energy warp the very fabric of space and time, a four-dimensional space-time, and that what we feel as gravity is simply objects moving along the curves and contours of this warped landscape. Planets orbit stars because they're rolling along a curved groove in space-time, like a marble in a bowl. Immediately, physicists raced to solve Einstein's fiendishly complex equations to see what they predicted about the universe. Just a year later, in 1916, the German physicist and astronomer Karl Schwarzschild found a solution. He calculated how spacetime would curve around a single, perfectly spherical, non-rotating ball of mass. His solution was radical. It contained something astonishing, a prediction that if you compressed a certain amount of mass into a sufficiently tiny point, spacetime would curve so severely that it would pinch off entirely from the rest of the universe. This pinched-off region, bounded by an event horizon, was the first mathematical description of what we now call a black hole. At its heart, his equations pointed to a singularity, a point where density and curvature become infinite, and the laws of physics as we know them simply break down. But Schwarzschild's solution, in its pure, elegant, mathematical form, was like a perfectly symmetrical jewel. Let's dive deeper into this elegant, symmetrical jewel of a solution and unpack exactly what it means. Because this is where the magic happens, where pure mathematics whispers secrets about reality that our everyday minds can scarcely imagine. To really get it, we need to step back for a moment and appreciate what Karl Schwarzschild was actually holding in his hands. He wasn't looking at a telescope image or a piece of rock. He was staring at a set of equations, Albert Einstein's field equations for general relativity. These are some of the most complex mathematical relationships ever conceived by humanity. They describe how the very fabric of the universe, space and time itself, curves and stretches in response to mass and energy. Solving them for a real-world situation is like being given a description of how all wood and metal and physics work, and then trying to calculate the exact shape of a specific, intricate chair. What Schwarzschild did was a feat of genius. He asked the simplest, most profound question. What is the shape of spacetime around a single, perfectly round, non-spinning ball of mass? Imagine taking a star like our Sun, and imagining it is perfectly smooth and still. How does its mass warp the universe around it? His answer was the Schwarzschild solution. And this solution is more than just a formula, it's a detailed map, a complete geometric description. It tells you how time ticks at every point near this mass. It tells you how space is stretched. If you were to draw this map, you'd find that close to the center of this mass, the lines of the map start doing very, very strange things. They begin to converge, to twist, in ways that suggest something extraordinary. Schwarzschild discovered that if you could theoretically squeeze that mass down small enough, into an infinitesimally tiny point, the map would break. The geometry would become so extreme that it would create a boundary in spacetime, the event horizon. Inside that boundary, the mathematics pointed to a place where the curvature became infinite, a singularity. This was the first rigorous prediction of a black hole, though the name wouldn't come for decades. It was all there in the math, a point of no return, and a point of no return to, a place where physics as we know it stops. Now, here's the critical thing about this mathematical map, this perfectly symmetrical jewel. It was a snapshot of a geometry, not a story. It described the shape of spacetime around this extreme object, but it didn't come with an arrow. It didn't say, time flows this way. And this is a weird and wonderful property of many of the most fundamental equations in physics. They are often time-symmetric. What does that mean in plain language? It means the math works just as beautifully if you imagine time running forward or backward. Let's make that less abstract. Think of a simple physics equation that describes a perfectly elastic ball bouncing on a perfectly hard floor. If you film that bounce and play the film backward, what do you see? You see a perfectly elastic ball bouncing on a perfectly hard floor. The motion obeys the same laws of physics forward and backward in time. There's no way, from the physics alone, to tell which is the real direction of time. That's time symmetry. Now, in our daily lives, we know time has a direction, we remember the past, we anticipate the future. We see a glass shatter, but we never see the pieces leap off the floor and reassemble into a glass. That's because of something called entropy, the tendency of things to move from order to disorder, which gives us an arrow of time. But the underlying, fundamental laws of motion? They often don't care about that arrow. They are reversible. So Schwarzschild's beautiful, pristine solution was like that film of a bouncing ball. It described a geometry that just was. But physicists, being storytellers at heart, immediately started to impose a story on it. The story of collapse. They imagined a massive star running out of fuel, its own gravity crushing it inward, falling past that event horizon, and ending up as a singularity. That story made profound sense. It gave the mathematics a compelling, real-world origin. It painted a picture of a cosmic trapdoor. That story gave the object a future, things fall in. But because the math itself was time-symmetric, there was another, equally valid story hidden inside it. You could play the film backward. What does playing the black hole film backward look like? Let's walk through it step by step. In the forward story of a black hole, you start with matter scattered in space. It collapses inward. It crosses the event horizon, moving inward. It ends up crushed at the singularity. The singularity is the future endpoint for anything unlucky enough to fall in. The event horizon is a one-way door you can only pass through going inward. Now, rewind that film. What do you see? You start with a singularity. Suddenly, matter and energy are not being crushed into it. They are being expelled from it. They are moving outward. They travel from the singularity, moving outward, until they reach the event horizon. And here's the flip. In the reverse film, the event horizon is still a one-way door, but now it's a door you can only pass through going outward. Nothing from the outside can cross it going in. The matter and energy from the singularity cross this horizon from the inside and fly out into the universe. The singularity, in this story, is not the grim future endpoint, it's the mysterious past source. It's where everything coming out of this object originally came from. This reversed object is the white hole. It is the black hole's reflection in the mirror of time. The mathematics of Schwarzschild's solution contains both pictures with equal validity. The singularity is there. The event horizon is there. But the flow of cause and effect, the "which way does the traffic go?" is completely inverted. In a black hole, the horizon is a point beyond which your future is forced toward the singularity. In a white hole, the horizon is a point beyond which your past is connected to the singularity. If you were somehow inside a white hole, your past would be that central singularity, and your future would be freedom in the outside universe. But if you were outside a white hole, no matter how hard you tried, you could never get in. Your rockets would be useless. You could fire probes at it. They would approach the horizon and then appear to slow down, frozen in time, never quite crossing. The white hole repels the entire external universe. It is the ultimate keep out sign in the cosmos. Think of it like a cosmic fountain versus a cosmic drain. A black hole is a drain in the bathtub of spacetime. Water, which is matter and light, swirls around it and goes down the pipe. The drain's edge is the event horizon. Once a bit of water passes the rim, it's gone for good, headed for the pipe below, the singularity. A white hole is that same plumbing, but with the film reversed. The water is erupting up from the pipe, pushing past the rim of the drain, and spraying out into the bathtub. The rim is still a special boundary. Water only moves outward across it, never inward. You can't push water back down into a fountain, it just won't go. That's the white hole, a fountain of spacetime, with its source buried in the inaccessible past. So, Schwarzschild's solution was a revelation. It showed that if you take Einstein's description of gravity seriously and follow it to its most extreme conclusion, you don't just get pits in spacetime. You get a symmetric pair, the pit and the peak. The trapdoor and the spring. The infinite sink and the infinite source. The black hole, which consumes, and its perfect mirror image, the white hole, which expels. They are linked by the simple, profound act of reversing time in the equations. One represents a possible future of matter, collapse and oblivion. The other represents a possible past of matter, eruption and creation. They are the yin and yang predicted by the geometry of gravity itself, forever entwined in the mathematics, challenging us to decide if our universe makes use of both, or if one remains forever a ghost, a beautiful mathematical possibility locked outside our physical reality. For decades, this was seen as little more than a curious mathematical artifact. The real object was the black hole, which physicists could imagine forming from the dramatic collapse of a massive star at the end of its life. But the white hole? It seemed to have no plausible origin story. Playing a star's collapse backwards to get an explosion that assembled a star looked as physically nonsensical as unscrambling an egg. It violated the second law of thermodynamics, which says the universe tends toward disorder, or higher entropy, not toward neat, ordered states. So, white holes were relegated to the back shelves of theoretical physics, interesting but not serious. The picture got more intriguing, however, as mathematicians explored the Schwarzschild solution more completely. In 1960, Martin David Kruskal extended the description to cover all possible domains of space and time. This, maximally extended, Schwarzschild solution revealed a stunning structure. Let's unpack that intriguing picture piece by piece, starting with Martin Kruskal's monumental act of cartography. Remember, Carl Schwarzschild had given us the first precise map of the spacetime around a dense, spherical mass, but it was a map with torn edges and confusing notes. It had coordinated singularities, places where the mathematics blew up not because physics was breaking, but because the specific system of labels, the Schwarzschild coordinates of t and r, became useless. The most famous of these was at the event horizon itself. It was like trying to use a standard street map at the North Pole. Longitude lines converge, and the concept of going north vanishes. The map said time and space switched roles inside the horizon, which was profoundly weird, and it only described the perspective of an outside observer, forever frozen watching things approach but never quite cross that boundary. What Martin Kruskal, and independently, George Zacharias, did in 1960 was something truly brilliant. They didn't change the landscape, they invented a whole new, better way to draw the map. They created new coordinates. Imagine them as a revolutionary new type of graph paper, where every single point, except the true, central singularity, is represented smoothly. No more torn edges, no more meaningless infinities at the horizon. In this new, maximally extended, map, you could finally plot paths that seamlessly cross the event horizon in a finite, sensible way. You could see the entire, hidden structure of the spacetime that the Schwarzschild solution implied all along. And what a structure it is! When you draw this complete Kruskal-Zacharias diagram, a stunning, symmetrical pattern emerges, divided into 4 distinct regions by the cross of light cones that represent the event horizons. In the traditional right-hand quadrant is our familiar universe, Region I. This is us. Here, outside the black hole, life proceeds normally. Below it, in Region II, is the interior of the black hole. Once you cross the diagonal line from our region into this one, your fate is sealed. All paths lead inexorably downward to the crushing singularity at r equals 0. So far, so expected. But the symmetry of the equations demands a mirror. On the left side of the diagram, we find 2 more regions. Region 4 is a perfect mirror image of our own universe, another asymptotically flat spacetime, completely separate and unreachable from our Region 1 under normal circumstances. And below it, in Region 3, is the time-reverse mirror of the black hole interior, the white hole interior. Here, the singularity sits in the past. Everything within this region is being ejected outward, forced to cross its event horizon into either of the 2 external universes. This is the eternal white hole twin, an object that, according to this pure mathematical structure, has always existed and is forever spewing matter and light out into the cosmos from its singular birth. Now, here comes the really fun, science fiction part. This maximally extended diagram doesn't just show 4 separate zones, it suggests they are connected. If you take a single snapshot of this entire spacetime at a given instant, a constant time slice, the geometry doesn't look like 4 separate sheets. Instead, it looks like a tube, a bridge, connecting the 2 exterior regions, our universe I and the mirror universe 4. This bridge has a throat, a narrowest point, and it connects 2 mouths. One mouth in our universe is the event horizon of the black hole. The other mouth in the mirror universe is the event horizon of the white hole. This is the famous Einstein-Rosen bridge, the original theoretical model of a wormhole. Picture it like this. Imagine 2 distant sheets of paper lying flat, representing 2 separate universes. Now pinch a spot on each sheet and pull them toward each other, connecting them with a short, 3-dimensional tube. The surface of that tube is the bridge. That's the embedding diagram of the Schwarzschild wormhole. The tantalizing idea is that matter falling into the black hole mouth in our universe might, in principle, travel through this bridge and be ejected out of the white hole mouth in another universe. It's the ultimate cosmic shortcut and the perfect plot device for 1,000 stories. But there's a devastating catch. Actually, there are 2. First, this beautiful, symmetrical Kruskal diagram describes an eternal black hole and white hole, a perfect, unchanging structure that simply exists forever. It's a mathematical ideal, like a frictionless surface or a perfect sphere. Real black holes, as we understand them, aren't born eternal. They are formed from the violent collapse of a massive star. In the mathematics of a formed black hole, the white hole region and the other universe are essentially cut out of the picture. They were part of the spacetime's infinite past, but the actual collapse process removes them from physical reality. So, the eternal bridge might not correspond to anything real. Second, even if it did exist, the bridge is catastrophically unstable. The moment you try to use it, the geometry collapses. Think of that tube connecting the 2 sheets of paper. In the Kruskal geometry, this tube isn't static. As time progresses, in a certain coordinate sense, the throat of the wormhole pinches off at the speed of light. It closes up instantly. The two mouths separate so rapidly that not even a beam of light, traveling from our universe's black hole mouth at the instant the bridge forms, could race through the tunnel fast enough to reach the other side before the white hole mouth slams shut forever. It's a door that closes faster than anything can move through it. Hence, it's dubbed non-traversable. And the final, most brutal nail in the coffin for interstellar travel is the singularity. Even if the bridge didn't collapse, any hopeful traveler would still have to pass through the very center of the black hole, the point of infinite density and curvature where known physics dies. There is no survivable path through that. So, the Einstein-Rosen bridge, while a breathtaking mathematical feature, is a cosmic dead end, a beautiful shortcut to nowhere. This is where our story makes that crucial pivot from pure mathematics and into the turbulent, paradoxical frontier where gravity meets the quantum world. For decades, whiteholes remained a curious, unrealistic footnote because they had no plausible creation story in classical, non-quantum, general relativity. But then, Stephen Hawking turned black hole physics on its head. He asked the quantum question of a classical object: what happens near the event horizon when you consider the frantic, probabilistic dance of quantum fields and the severe curvature of space? His shocking answer was Hawking radiation. Empty space, according to quantum theory, is not empty. It's a seething foam of virtual particles, particle-antiparticle pairs that constantly pop into existence and almost instantly annihilate each other, borrowing energy from the universe for a fleeting moment. Hawking realized that if this happens right at the precipice of a black hole's event horizon, a bizarre theft can occur. One particle of the pair could fall in, while the other escapes. The escaped particle becomes real, stealing a tiny bit of the black hole's mass energy to pay its debt to the universe. From afar, the black hole appears to glow with a faint, thermal heat, Hawking radiation. And slowly, over eons, it evaporates. This solved one huge puzzle. Black holes have a temperature and obey thermodynamics, but created an even deeper, more profound crisis: the information paradox. Quantum mechanics is built on a sacred rule: information is never destroyed. It can be scrambled, hidden, or rendered hopelessly complex, but it must, in principle, be preserved. If you burn a book, every letter, every word is encoded in the position, momentum, and energy of the smoke particles and ash. A hypothetical, infinitely powerful computer could, in theory, reverse the process and reconstruct the book. Now throw that book into a black hole. According to Hawking's early work, the radiation coming out is purely thermal. It's random heat, like the glow from a stove. It carries no information about what fell in, whether it was a book, a star, or a truck full of feathers. When the black hole finally evaporates completely, leaving behind only that random radiation, what happened to the detailed quantum information of the book? It seems to have been erased from reality, violating the core principle of quantum mechanics. This was the nightmare. This paradox is the catalyst that brought white holes roaring back from the realm of mathematical curiosities. Theorists began to ask, what if Hawking radiation isn't the end of the story? What if evaporation is just a phase? The key lies in considering the final moments. As a black hole evaporates, it shrinks. Its mass decreases, and its event horizon gets smaller and smaller. When it gets down to an almost inconceivably tiny size, somewhere around the Planck scale, a length of about 10 to power minus 35 meters, the scale at which quantum gravity effects are believed to dominate, classical general relativity's prediction of a point-like singularity must break down. Space and time themselves are expected to become grainy, quantized. The infinite curvature is likely smoothed out by quantum effects. In this wild, uncharted domain of quantum gravity, a fascinating possibility emerges: a quantum bounce. The idea is that the black hole's collapse doesn't end in a timeless singularity. Instead, when compressed to this ultimate density, quantum pressure or the discrete nature of spacetime itself creates a powerful repulsive force. The collapse halts. And then it reverses. Like a compressed spring recoiling, the spacetime geometry undergoes a quantum transition, a tunneling event, from a black hole configuration to a white hole configuration. Think of it not as a classical, continuous reversal, but as a sudden, probabilistic quantum leap. The black hole, in its final, microscopic state, transforms into its time-reverse twin. This isn't the eternal white hole of the Kruskal diagram. It's a new, formed white hole, born from the quantum ashes of an evaporated black hole. The beautiful consequence of this black hole to white hole transition is that it saves the information. The white hole, by its very definition, is an emitter. After the bounce, this newly formed white hole would then, over another immense stretch of time, radiate out its contents. But this wouldn't be the random Hawking radiation. Instead, it would radiate out all the mass energy, and crucially, all the quantum information, that the original black hole had swallowed during its lifetime. The information isn't lost in a singularity or locked in random thermal photons. It's preserved through the bounce and eventually released back into the universe. The paradox, at least in this proposal, is resolved. Of course, this is still highly speculative, resting on theories of quantum gravity we haven't fully formulated. But it gives white holes a potential, profound purpose in our cosmos. They are no longer just mathematical mirror images. They become potential cosmic safety valves, ensuring the universe doesn't violate its own quantum rulebook. They transform from being impossible beginnings to possible, even necessary, endings, the final phase in the life cycle of a black hole, where everything it ever consumed is finally given back. This is not just wishful thinking. It's a scenario actively pursued within specific frameworks of quantum gravity, most notably in loop quantum gravity, LQG, a theory co-developed by the Italian theoretical physicist Carlo Rovelli. In LQG, spacetime isn't a smooth continuum but is woven from tiny, finite loops. This granular structure prevents the formation of a true, infinite singularity. Rovelli and his colleagues have worked on models showing how the interior of an old, evaporating black hole could quantum tunnel into the interior of a white hole. From the outside, for a very long time, it would still look like a black hole. But inside, the story would have already changed. This leads to the next logical, and utterly mind-bending, question. If black holes are turning into white holes, why don't we see these cosmic fountains lighting up the sky? Alright, let's really dig into this mind-bending question. We've just wrapped our heads around this incredible idea. A tiny, ancient black hole could, at the end of its life, hit a quantum wall and bounce, turning inside out to become a white hole. It's a cosmic metamorphosis. So, the very next thought should be, well, where are they? If this is happening, why isn't the universe full of these spectacular, matter-spewing fountains? Why haven't our telescopes caught a single one putting on a show? The answer is one of the most profound and strangely beautiful predictions of Einstein's general relativity, and it messes with one of the most fundamental things we think we know, the flow of time itself. We all operate under the assumption that time is universal, that 1 second for me is 1 second for you, is 1 second for a star a million light-years away. It feels absolute. But Einstein revealed that this is an illusion of our everyday, low-gravity lives. Time, it turns out, is more like a river than a clock. And a river can flow at different speeds in different places. The key is gravity. Gravity, in Einstein's view, isn't just a force that pulls on things, it's the curvature of spacetime itself. Imagine spacetime as a vast, stretchy trampoline. A heavy object like a star sits in the middle, creating a deep dip. Now, think of time as being woven into the fabric of that trampoline. Where the dip is deepest, where gravity is strongest, the very fabric of time gets stretched out. Clocks tick slower there. This isn't a mechanical malfunction, it's the nature of reality. The stronger the gravity, the more time slows down. This is gravitational time dilation. We can actually measure this effect here on Earth, believe it or not. Atomic clocks, incredibly precise timekeepers, run ever so slightly faster on the top floor of a skyscraper than they do in the basement. Why? Because at the top, you're a tiny bit farther from Earth's center of mass, so gravity is very minutely weaker. The difference is infinitesimal, fractions of a second over a human lifetime, but it's there, and it confirms Einstein was right. GPS satellites in orbit have to constantly correct for this effect. Their clocks run at a different rate than clocks on the ground because they're in a weaker gravitational field. If they didn't, your phone's map would be off by miles and minutes. So, time dilation isn't science fiction, it's engineering reality. Now, take this concept and crank it up to its ultimate extreme, the edge of a black hole. A black hole is the deepest possible well you can imagine in the space-time trampoline. Its gravity is so intense that at the point of no return, the event horizon, the stretching of time becomes infinite from an outside perspective. Let's unpack what that really means. Imagine you have a brave, indestructible astronaut friend. She volunteers to fly her spaceship toward a black hole. You, being sensible, stay in your spaceship far, far away. As she gets closer and closer to the event horizon, something utterly bizarre happens from your point of view. You're watching her through a powerful telescope. You see her ship's clock, which is broadcasting a signal. As she approaches the horizon, her clock appears to tick slower, and slower, and slower. Her movements become like molasses. The light from her ship gets redder and redder. This is the gravitational redshift, a cousin of time dilation. From your distant vantage point, she never actually crosses the horizon. She just asymptotically approaches it, fading and slowing, becoming frozen in time at the threshold. To you, the crossing takes an infinite amount of time. But what about for her? From her perspective inside the ship, her clock ticks normally. 1 second feels like 1 second. She doesn't feel any sudden slowdown. She crosses the event horizon in a finite, and perhaps quite brief, amount of her time. There's no dramatic barrier, no shimmering wall. She just passes through a point of no return, and after that, the geometry of spacetime is such that all paths lead inevitably inward to the singularity. The difference in experience isn't an illusion, it's a fundamental feature of a curved universe. There is no single now that applies everywhere. This brings us back to our dying black hole and its quantum bounce. The theories that propose this bounce suggest it happens when the black hole has evaporated down to a nearly unimaginable scale, the Planck scale. At this point, the black hole is incredibly tiny and incredibly dense. For the physics at that location, the bounce itself, the moment of transition from a black hole state to a white hole state, might be a very rapid event. Let's say, for the sake of imagination, it takes about 1 microsecond in the frame of reference of the matter and energy right there at the core. But here's the cosmic catch: where is that core? It's at the heart of a region of unbelievably strong gravity. It's at the bottom of the deepest gravity well in the universe. And because of the extreme time dilation we just described, events that happen quickly down there are stretched out across an immense duration for anyone watching from the outside universe, for us. Think of it as a cosmic message in a bottle. The bounce happens in a microsecond and sends out a signal, the first burst of radiation from the new white hole. But that signal has to climb out of this infinitely deep gravity well. And as it climbs, it fights against the stretching of time. Every photon of that signal is redshifted into oblivion. Its energy is sapped. From our perspective, that 1 microsecond event is smeared over an almost unthinkably long period. How long? The calculations are staggering. For a stellar mass black hole, one formed from a collapsed star, with a mass several times that of our Sun, the Hawking radiation evaporation process itself would take on the order of 10 to power 67 years. That's a 1 followed by 67 zeros. The current age of the universe is about 1.4 by 10 to power 10 years. So, we're talking about a timescale that is 10 billion 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 times longer than the universe has even existed. And the final bounce and white hole phase? That gets stretched over a comparable, mind-numbing duration. So, when we look out at the sky at known black holes, like Cygnus X1, we're looking at infants. Cosmic newborns. They've been around for a few million or billion years, which is less than the blink of an eye compared to their total potential lifespan. In our frame of reference, they haven't even begun to evaporate in a meaningful way, let alone reach the quantum bounce stage. Their potential white hole phase is an event placed so far in our future that it might as well be forever. The stars will have burned out, galaxies will have drifted apart, and the universe may have settled into a dark, cold, dilute state long before any stellar mass black hole we see today makes its transition. This is the ultimate reason we don't see white holes lighting up the sky. It's not that they aren't happening, it's that, from our temporal vantage point, they are events of such incomprehensible slowness that they are effectively frozen in the future. The universe we live in is simply too young, and our clocks run far too fast relative to the deep time clocks ticking at the hearts of these black holes, for us to have witnessed a single one of these grand finales. It's a humbling thought. It means the cosmos has dramas unfolding on timescales we can hardly conceive of, a symphony where one note is held for longer than all of history. The black holes we see are not eternal monsters. They may be slow-motion seeds, and their magnificent, white-hole final acts are stories written for an audience in a future so distant that it redefines the word future. Their light show isn't absent, it's just scheduled on a calendar where the page turns once every trillion years. So, this is where theory meets the practical challenge. Is there any chance they exist in reality? And can we find them? This is the multi-billion-dollar question. Scientists have proposed several ways we might spot a white hole, though all are incredibly challenging. One signature would be a sudden, incredibly powerful, and brief explosion of very high-energy radiation, like a gamma-ray burst. If a small, primordial black hole finished its evaporation and popped into a white hole, the release of its remaining trapped energy could be spectacular. Astronomers have detected mysterious gamma-ray bursts for decades, and while most are explained by other phenomena like neutron-star collisions, it's conceivable that a few could be the death cries of black holes turning white. The trick would be finding a burst with a specific, predicted energy signature that doesn't match any other known source. An even more radical idea, championed by Carlo Rovelli, is that these final-stage white holes might not explode dramatically at all. After the quantum bounce, what's left might be an incredibly tiny, stable object with a mass of about a microgram, the weight of a human cell, but containing a vast, hollow interior where all the swallowed information is stored. This object would interact with the universe almost exclusively through gravity. It would be dark, tiny, and everywhere. Rovelli has speculated that such objects, the fossil remnants of primordial black holes, could constitute a portion of the mysterious dark matter that holds galaxies together. If true, white holes wouldn't just be rare cosmic oddities. They would be a fundamental, hidden component of the universe's mass. Finding one would then mean detecting a particle-like object with a tiny mass but no other interactions, a monumental technical challenge, but one that physicists are beginning to contemplate with designs for ultra-sensitive quantum-based detectors. There's also the most profound speculative connection of all, the Big Bang itself. Some have noted that the mathematics of a white hole singularity, an event where matter and energy erupt from a singular point in spacetime, bears a striking resemblance to the mathematical description of the Big Bang. Could our entire universe be the interior of a white hole that erupted from some other cosmos? This idea fits into big bounce or cyclical universe models, where a previous universe collapsed into a supermassive black hole/singularity, which then rebounded as a white hole, our Big Bang. It's a breathtakingly poetic idea, that every black hole in our universe might contain, in its distant future, the seed of a new cosmos, and that our own universe might be the white hole offspring of another. Now we must balance this excitement with a heavy dose of scientific reality. The majority of physicists remain deeply skeptical that white holes exist in our universe. The core objection is still the one from decades ago. There is no known natural process to create one. Stellar collapse makes black holes, not white holes. While the quantum bounce idea is compelling, it relies on theories of quantum gravity that are not yet proven or complete. Furthermore, even if a white hole did form, it might be violently unstable. Any tiny speck of cosmic dust falling onto its horizon would, according to some calculations, have the effect of collapsing the white hole structure back into a black hole. In a universe filled with dust and gas, a long-lived white hole might be impossible. So, where does that leave us? In a state of wonderful, tantalizing uncertainty. White holes are a brilliant consequence of our best theory of gravity. They are a potential savior for our best theory of the very small from a paradox posed by black holes. They offer a possible link to dark matter, to the origin of our universe, and to tunnels across the cosmos. They represent the power of theoretical physics to explore landscapes of reality far beyond our current observational reach. They teach us that the universe, in its fundamental code, might be symmetric and beautiful in ways we are only beginning to glimpse. The search for them, whether in the flicker of a gamma-ray burst or in a futuristic quantum sensor, is a search for a new chapter in physics. And that, my friends, is the story of Whiteholes, from a forgotten line in Schwarzschild's equations to a potential key for unlocking the secrets of quantum gravity, dark matter, and the origin of everything. It's a reminder that the universe is stranger, more imaginative, and more full of possibility than we can often conceive. The black hole was once a mathematical curiosity dismissed by Einstein himself. Today, we have a picture of its shadow. Perhaps the white hole is on a similar journey. If this exploration sparked your curiosity, if it made you look up at the night sky and wonder what else is out there, hiding in the math and waiting to be found, then do me a favor, give this video a like. It really helps the channel. Subscribe if you haven't already, and ring that notification bell so you don't miss our next journey to the edge of understanding. And please, I'm genuinely curious. Drop a comment below and tell me where you're watching from and what time it is for you. Are you having a morning coffee in Toronto? A late-night study session in Tokyo? Let's see how far our community of the curious spans. Thank you so much for watching and for spending your time exploring these cosmic ideas with me. Until next time, keep looking up, keep asking questions, and never stop wondering about the beautiful, bizarre universe we call home. Good night wherever you are. Peace.